if you want.
So let me do it. It seems to be working again.
Indeed. Okay, Daniel, would you be sort of prepared to start after I introduce you?
Anytime.
All right, excellent. So welcome everyone to the latest iteration of the One World Probability Seminar. Today we're going to hear from Daniel Ueltschi and Cécile Mailler, starting with a talk by Daniel on the cycle lengths of random permutation models. Daniel, go ahead.
Well, thank you. Thanks a lot to Peter and to Dominic for organizing this wonderful seminar, and indeed for inviting me and Cécile. So I'd like to discuss indeed cycle lengths random permutation models. And this is joint work with Jakob, who is also here, Jörg Fröhlich, and the second work with Jakob again, Cécile, and also Peter Mörters. Let me just, here describe the menu. So first I'm going to explain what the random interchange model is. It's a probability model about products of transpositions. I will have 2 slides on relations to the quantum Heisenberg model. I mentioned it's only 2 slides. I don't want to scare everybody, anyone away. Then I will discuss the cycle lengths, and there are quite a few results, many conjectures. So I'm going to review what has been proved, at least, most of the works which has been proved, and you will see that there are lots of holes in our knowledge. And then, as we will see, we can gain some partial understanding, which basically amounts to understanding the Bernoulli convolution of a certain random partitions, and we would like to understand the random partition. And I'm going to explain how we can indeed characterize, to some extent, random partitions using Bernoulli convolutions. And then I will discuss further open questions at the end. By the way, please ask any question that come to your mind anytime. I'm very happy to be interrupted by your question. All right, so let me discuss the random interchange model, also called the random storing model. And this can be viewed in the following way. You have a graph with vertices, sets of vertices, and set of edges. And then let's draw a sequence of random edges independently, identically, uniformly. So we have E1, E2, EK. So all those are edges. The number of edges we pick up is also random, and it's given by a Poisson random variable with parameter beta. So beta is going to be one of the parameters. And since we are going to scale, the interest will be to take the graphs to be larger and larger. The correct scaling will be beta times the number of edges. Okay, so we have a sequence of edges in the graph, and we construct the following random permutation. That's the composition of transposition. So we start with the transpositions of the sites at the end of E1. We compose with the transpositions of E2, and so on. So then this gives a permutation of the sides of the graph. Once we have a permutation, the main interest is the cycle lengths of the permutations. So here you have a vector of cycle lengths. C1 is the largest cycle, And the cardinality means that we look at the number of sites in the largest cycle, and we divide by the cardinality of the graph. So this is less than 1. This should be clear. If you have a single cycle, then the length of the cycle is just the number of sites. So you get these numbers. They are all less than 1. They decrease by definition. And also they all add up to 1. Because if you add all the cycle lengths, then basically you have accounted for every site once. So you get just the number of sites, and we have divided by exactly what we need. So here we get a random partition of interval 0, 1. And what we would like to understand is, in some cases, for specific graphs, always very large graphs, to understand the structure of this random partition. And there is a variant which turns out to be very relevant for connections to, for instance, to quantum systems. We weigh this sequence of transpositions, I mean this permutation, using this kind of weight. We have an additional parameter theta, and then we weigh with theta to the number of cycles. So then the expectation with this product of transpositions, I mean this random permutation constructed like that, with parameters theta and beta, so the expectation of this thing is like the expectation of the object we constructed before, with the theta equals 1. So in fact, no extra weight. And then we have the expectation that then we put this theta to the number of cycles, the function, and we normalize, I mean, we divide by the correct normalization, so that this is still the expectation coming from the probability measure. And doing this by putting this theta to the number of cycles changes quite a lot. I mean, the typical permutations will be different because of this additional weight. And so now we have a new way of defining random permutations, and this also gives us a probability on permutations. We can look again at the sequence of the cycle length divided by the volume, I mean by the number of sites, and we would like to understand this random partition. Now, my 2 slides on the links to the quantum Heisenberg model. I hope I'm not scaring anyone. So here we can also define this model of quantum spins on a graph. So suppose you have a graph, V and E. We consider the Hilbert space, which is given by a tensor product of C2s. Or if you wish, you can also imagine that you consider Ising configurations on those vortices, and you look at the space given by the little L2 of those configurations. On C2, we have spin operators given by the Pauli matrices. So we have sigma 1, sigma 2, sigma 3. And this allows to construct the Hamiltonian, which is given by a sum over the edges. So ij represents an edge. And then given an edge, we look at this kind of interactions. We take the spin operator acting at the site I times sigma j, I mean sigma acting at j, and this is the one operator in the Pauli matrices like that. We also have a sigma 2 term, sigma 3 at I and j, and this gives the so-called Heisenberg, quantum Heisenberg model. And here is a non-trivial relation. I mean, it's hard to do to get, but I don't claim that you should see it right away. This sum over this kind of Heisenberg interactions can also be written as a sum over twice the transposition operator at sites I and j. I mean, up to 2, and okay, we have a -1, which is not very important. So Tij is the transposition operator. meaning that when you apply it to a tensor product of two vectors, that's I and j, you get the same but in reverse order. Okay, so it so happens that we have this transposition operator. Let's accept it for now. And if we calculate the partition function of the quantum Heisenberg model, that's the trace of exponential minus beta h. So we can write it in terms of this transposition operator. So okay, we have something in front which is not so important. But otherwise, let's just expand the exponential using the Taylor series. So we sum over k. We have, something to the k divided by k factorials. And then we are going to get the sum over edges of this transposition operator raised to the k. So which amounts to summing over k edges. And taking the trace, we have a trace, and we have this product of transposition operators. Now, the fact is that this trace is exactly 2 to the number of cycles. Or more precisely, we sum over edges over here. Given these edges, we can construct the permutation which is given by the product of transpositions. And then you can count the number of cycles, and this gives exactly this trace of this product of transposition operators. So this is the identity which allows to make the link with those permutations before. So because of that, you get that this trace is equal to the expectation when we of a model before, where we sum over the number of transpositions, the number of edges, and then we consider the product of those transpositions, and we have this 2 to the number of cycles. So, and again, and so this expectation now is really the one before, with the number of transpositions being random, being Poisson, and the sequence of edges being IID with the right number. So this is a first very interesting identity, which was first proposed by Balintot in 1993, which is that the partition function is given by the normalization for this random interchange model. And actually, the connection is much deeper than that, because you can also look at the natural spin-spin correlations for the quantum systems, which are given by the trace. And then you take 2 spin operators at sites I and j, exponential minus beta h, you normalize by the partition function. And this is given precisely by the probability in this measure with the parameter 2. So everything is weighted by 2 to the number of cycles. And that's a probability of the natural permutation correlations, which is that 2 sites belong to the same cycle. So this is a very nice identity. The quantum spin correlations are given by the probability correlations of this random interchange or random storing model. And another identity which is also true is that that also works for, these are identities for all graphs. If you look at the magnetization, which is like the sum over these Pauli matrices in direction 3, we divide by the volume. So this is the average magnetization operator. And looking at this kind of things, it gives you some kind of Fourier transform or generating function or characteristic function for the magnetization. And so this gives very useful information about the system. And so this trace of the exponential of the magnetization, like that, when you average, is also given by the expectation with this random interchange model, where you take the product over all cycles and the cosine, and then you consider, well, this h is the same number as here, and then otherwise you have the length of the cycle, the j cycle, divided by total volume. So this thing here depends only on the cycle structure of the permutation. If we knew what random permutation we have, I mean, coming from this model here, then we would in particular know the generating function for the magnetization, which is something that we would really like to know in the quantum system. All right, so I mean, I don't expect you to fully understand, for instance, the left side here, but somehow the right side is going to come back later, where we have the expectation in this random permutation model of a product over all cycles of a function, which is like the cosine of something which involves only the cycle structure. All right, that's it for the quantum Heisenberg model. So now back to the permutations. Let me discuss some of the work. The main interest, I mean, and I will actually mention it, is to look at ZD, but ZD is a very complicated graph. So one has to be a bit more reasonable, and it's turns out almost no graph is trivial. So first, let me discuss the case of theta equals 1. So we do not have this extra weight on the cycle. So we just pick up edges at random and look at the composition, which gives, I mean, the permutation given by the composition. So on trees, when you consider regular trees of sufficiently large degrees, there are a bunch of results. The first, to prove the existence indeed of the phase transitions when you vary the parameter beta, was Omer Angel in 2003. And then there were a lot of questions left open for instance, whether there was a single phase transitions. And this was proved by Hammond in two papers in 2012, 2015. Then I have a paper with Jacob, and then even better results by Bert Seelert and Liz Roth in 2018. By the way, here you have a little bit illustration of what we are dealing with. Here you have a graph. So this is a tree of degree. The degree is 1 or 2. I'm not sure how we count the degree. The number of descendants is just 1, if you wish, but it's just for the illustration. And then on top of each edge, you have these extra time directions. And then we select some transpositions. And given a bunch of transpositions, you can look at the permutation. And then it amounts to following the trajectory like that. And so this point is sent to this one. And then you can look this point, I mean, it would be sent to this one, and so on. So that's one way to visualize quite conveniently those transpositions and those permutations. Anyway, so what Angel proved, and which was refined later, was indeed that if you're in a tree and beta is large, and also the number of descendants at every site is large enough, then you do have the possibility of going from the origins, following these trajectories, and going all the way to infinity. That's the kind of results on trees. On the complete graph, there's a lot of interesting things to say too. First, if you take beta to infinity, well, it's not hard to check, but for beta going to infinity, you actually go to uniform permutations. And then you have, one knows a lot about the cycle structure. But you can also ask more interesting questions about how fast you're going to reach the uniform permutation. And this was first studied by Diaconis and Shasharani. This is a very important paper in many respects. The results are not completely relevant to what we are going to discuss here. At the same time, they introduce several important techniques which have been used in the sequel. So this paper is important in many respects. And then they also look at other questions which are also very interesting. But what we are doing here in the complete graph is still to take beta finite. To tell the truth, it's beta over n that we should be looking at. to get something non-trivial. And also in terms of Erdős-Rényi, I mean, if you look at all those edges which have a chance to have been picked at least once, we are in the regime where we have a giant component, but not all the sites belong to the giant component. And then it was understood first by Aldhaus, who conjectured that if you look at the cycle structure, then this converges to Poisson-Dirichlet. But by the way, for beta going to infinity, you get uniform permutations, and then it's known that the cycle structure has Poisson-Dirichlet distributions. I will introduce what Poisson-Dirichlet is a bit later for those who don't know it yet. But here for finite beta, the situation is following. So you look at this random partition of 0, 1. Then there's going to be a large cycle, I mean a large partition element here. And as it turns out, it does not go to 0 or go to 1. So we get this larger partition element like that. The second largest is also of order 1. And then everything is going to get an accumulation point over here. And the accumulation point is given by the fraction of sites in the large component for Erdős-Rényi. So we take Erdős-Rényi with this parameter P, which is related to the beta. I mean, that's also the probability that the site has at least one, I mean, is touched by one cross. I mean, it shows up in the list of edges. And from this, you have a connected component. This connected component turns out to behave a bit like uniform permutation. I mean, it's not in a strong sense, but in terms of a cycle structure, it does. And then we have Poisson-Dirichlet distributions of the cycles in the large component. And for the rest, we have plenty of cycles of length 1. When we divide by the number of sites, which is assumed to be huge, I mean, that's really n goes to infinity, this thing. So all these things are tiny. In terms of partitions, it's 1 over infinity. So what we are really interested in is this first part, where we get this Poisson-Dirichlet. So this was understood by Aldhaus, and I mean, it's perhaps not so surprising that we are in a mean field situation and Poisson-Dirichlet is present there, but still, the mechanisms were not obvious. So it was actually a very clever insight by Aldhaus. And the proof was not easy to do, and there was a proof by Ueltschi in 2005. So this is indeed what happens for the complete graph. And there has been several additional works looking at exploring different aspects of the model on the complete graphs, or sometimes also a bit more generally, by Berestiki, Alon and Kosma, Berestiki, Kosma, and also a bit of a different situations by Björnberg, Kotowski, Lis, Miłosz, where the model also has the possibility of reversal. And then they prove that this is Poisson-Dirichlet parameter 1/2. I mean, something very interesting, but I don't have the time to go in this direction. So this is for the complete graph. And I'd like you to remember this structure over here, so that we have, I mean, a special parameter between 0 and 1, which depends on beta. And by the way, I forgot to say, this represents the fraction of sites in large cluster in Erdős-Rényi. And as you know, it depends on the value of this probability of picking up an edge. And it's only when this probability is, I mean, this parameter P is large enough that you get a large component. So indeed, we have a phase transitions for beta small. I mean, there's no real partition. All the elements are tiny. And when beta goes past a certain value, then we have a fraction of sites in large cycles, and then we have this Poisson-Dirichlet here. Okay, then you have further results in various graphs. There is, for instance, the hypercube. This was a compromise between, I mean, one would like ZD with a lot of spatial structure. With a hypercube, it's much easier because the number of neighbors grows as the system size grows. But at the same time, the diameter of this graph is infinite. So it's not so obvious to prove. And that's something that we did with Roman Kotecki and Piotr Miłosz. A Hamming graph, it's some kind of graph which, I mean, if you look at the diameter of a complete graph, it's 1. The diameter of Hamming is 2. But then Miłosz and Sengul could basically extend the results of Schramm also in this case, which has a little bit of spatial structure. Something I don't have much time to also explain, random regular graphs, recent very nice results of Boudevin, who prove also the occurrence of large cycles in this situation. On ZD is really what we would like to get. I mean, much more difficult, but of course very interesting. It so happens that one expects Poisson de Dirichlet, exactly the structure we had before, provided the dimension is larger or equals to 3. So if you are on Z3 or ZD with D larger than 3, then you expect the phase transitions depending on beta. For beta small, all the cycles are small, but then past the point, you have the occurrence of large cycles. Large cycles means macroscopic. So when by the way, when I'm mentioning ZD, what I have in mind is a large box in ZD, and we want to take the box to infinity. So then one expects cycle lengths to scale like the volume of this box. And in fact, the distributions of the large elements to be exactly like on the complete graph. Again, the Poisson de Dirichlet. So it's not totally trivial to convince oneself that this is indeed the fact. But there are numerical results which indeed back this conjecture. And that's something that we described in the paper with Christina Goldschmidt and Peter Windrich. And recently, there is an absolutely stunning result by Dorel Boehm and Alan Sly. They indeed prove, I mean, not Poisson de Dirichlet, that's one cannot ask for too much, but they indeed prove that on Z5, if you look at the probability of the origin and you look at where you end up after all those transpositions, there is positive probability of reaching infinity, provided beta is large enough. So this is actually an absolutely beautiful paper. I mean, very creative, and actually it's very impressive. So there is indeed, I mean, it also opens the way of proving much more information on ZD. And still on ZD, you have some interesting results. For instance, you can compare the probability of long cycles and the probability of large clusters, percolation clusters, in quite a natural way. And one can check that the critical beta is distinct for one and the other. So this was done by Peter Mühlbacher first, and recently by Betts, Klippel, and Kraft with more precise results. And another thing, I don't have too much time to explain also, that's another way of looking at things, which one can understand as the stability of Poisson de Dirichlet. And Joffe and Todt proved indeed that if you start with I mean, you have a graph, but you start with a uniform permutations, and you know that you have Poisson de Dirichlet, obviously. But then you run a split merge process for which the random interchange is the invariant measure. And you can check that at least for a while, the Poisson de Dirichlet structure will still be there. So that's quite a different, I mean, a very interesting approach from the other side, in a sense, to proving that Poisson de Dirichlet should be expected. Then let me discuss also the case where this parameter zeta differs from 1. So now we give a little bit of I mean, encouragements of having more cycles. So in fact, for data larger than 1, we expect smaller cycles. We expect more of them, so they will be smaller. So this is just to remind you about the definition of this measure when we have a zeta. And there are results on trees by Jakob and myself, and also by Betts, Ehlert, and Lies. And on Z2 one can prove the following thing. You can look at the probability that two sides belong to the same cycle, and then one can get an upper bound, which is like the power, an inverse power of the distance between the two sides. So in Z2, one should not expect large cycles. I mean, when the cycles are macroscopic, when you have a fraction of sides in the same cycle, it means that two very distant points have a positive probability of belonging to the same cycle. Here, the probability that two sides belong to the same cycle decreases with the distance, decreases at least like a power. And something which is both intriguing and extremely frustrating is that this is proved only for those parameters theta equals 2, 3, 4, I mean integers and not 1. And if it's true for theta equals 2 and theta equals 3, it seems quite clear that in between it should also be true. But there is definitely no proof. The proof goes by basically going back to the quantum system and using the method of Koma and Tasaki to prove the decay of correlation functions. I mean, this is the context of the Mormin-Wagner theorem. It's based on continuous symmetries. So this kind of bound for this cycle, I mean, for this random permutation system is proved thanks to the connections to quantum spins and to the symmetries we have over there. So that's why we have these funny connections. I mean, the connection to quantum spins is only when the parameters theta are 2, 3, and 4. I mean, I explained the Heisenberg model with theta equals 2. We have further quantum systems for larger integer values of theta. And for complete graph, we can get first the calculation of a free energy, which allows to calculate the transition parameter, or critical parameter, was done by Jacob. And then in a joint work with Jacob and Jörg Fröhlich, we proved the following thing, which is that if you take the expectation of this kind of function on cycles, so it's 1 over theta, exponential h, and the cycle length of, the length of a J cycle divided by the number of points, and plus theta minus 1. So the whole thing converges essentially to the same expectation with Poisson-Dirichlet. So we would like to say that when we have this model with theta to the number of cycles on the complete graph, we should have Poisson-Dirichlet of parameters theta. But nobody has proved that Poisson-Dirichlet is indeed present. What can be proved, and this is a calculation using the spins, in fact, is that this expectation of this function of cycles converges to the same expectation with Poisson-Dirichlet. So the question is, can we claim that thanks to this, we have characterized Poisson-Dirichlet enough so that we are sure that Poisson-Dirichlet is indeed the only one? So this is the context of what I'm going to explain with these Bernoulli convolutions. Basically, suppose you have a random partition, and suppose you have this kind of expression, expectation with your random partitions of something of this kind. And we would like to say that if this coincides with the expectation of Poisson-Dirichlet, we would like to conclude that we must have Poisson-Dirichlet. And well, we will. I don't tell you what we are going to, what I'm going to claim. So now I'm discussing the Bernoulli convolution for random partitions. First, let me define the Poisson-Dirichlet distribution. We consider a partition written like that. So we have x1, x2, and so on, with the x's being ordered. They are non-negative numbers, and they add up to 1. In fact, it's easier to construct a slightly different random partition called the Griffiths-Engen-McCloskey, or GEM distribution. And the picture works like that. First, you pick up a number at random, uniformly, let's say something like that, and you decide that this gives you your x1. And then with what remains, you pick up a number at random, let's say random between the endpoint here and 1, like that. And this interval over here, you decide that it's x2. And then in what remains, a number at random, and this is x3, and so on. So like that, you are getting numbers. They're all non-negative. They're all getting smaller and smaller, at least in average. And they add up to 1 by construction. And this, the random partition you get out of that has the so-called gem parameter, so gem distribution of parameter 1. This is this gem 1 distribution. And as you see, I mean, something which definitely makes it a bit different from the from Poisson-Dirichlet is that this sequence of numbers is not ordered from the largest to the smallest. Well, just order it from the largest to the smallest, and you get Poisson-Dirichlet of parameter 1. And I mean, for those who are interested, you can also get to jump from Poisson-Dirichlet with a size-biased pick. So you pick up the terms one by one according to their size, and then you also tilt them towards choosing them the largest first, but not strictly. And this is a one parameter family of distributions, because one can also do it in a more systematic fashion. Actually, that's also this so-called residual allocation distribution. You say you can choose an arbitrary distribution for x1, and then the rule is that now you have a smaller interval left. You scale it back to 0, 1. You use exactly the same distribution to pick up something, scale it down, and this gives you your next element. And then in what remains, scale it back to 0, 1. Use the same distribution as before, scale it down, and this is the so-called residual allocation, which depends on a single distribution of 0, 1. And for Poisson-Dirichlet, if for this distribution you take a beta random variable, then you get Poisson-Dirichlet of parameter theta. And beta random variable of parameters 1 and theta. For some reason, 1 is relevant here. Then you get Poisson-Dirichlet of parameter theta. Okay, and here you have the construction if you wish. I mean, you can also pick up those numbers, I mean, those random variables IID, and then these things corresponds to this kind of sequence. X1 is Y1, but then you have the next one here. You have to take Y2, but you scale it with the length here. And for the next one, you take Y3, but you have to scale it, and scale it means basically you scale it once and scale it twice. So it's 1 minus Y1, 1 minus Y2. One can check that this gives exactly this stick breaking or residual allocation construction. So this is, that's the Poisson-Dirichlet or gem construction. Now, we would like to characterize them using random coloring or with these Bernoulli random variables. How do we do it? Well, the idea is that you have this random partition. Now, we consider a sequence of IID Bernoulli random variables of parameter P. And we look at this new random number. So we sum over all the i's, and we have xi, but times epsilon I. So epsilon I is 0, 1. So we take it on that. Y is obviously a random variable in 0, 1. And the distribution of Y is related to these questions we had before. Because let's look at the characteristic function of Fourier transform for the random variable Y. So you have here the expectation. Expectation means expectation on X and on epsilons. Then this is the expectation. I mean, I'm just using this equation here. Now, from here to here, I'm going to actually write explicitly the average of those Bernoulli random variables. And you can check that this thing you're going to get either, I mean, epsilon j can be 1, in which case you take it, or 0, in which case you get 1. So you get like p times this plus 1 minus p times 1. And if you, okay, put some prefactor, I mean, you extract this thing and you put it up front, then you get exactly the expectation of a cosine. So actually this corresponds to p equals 1/2. So you have like 1/2 this thing. I mean, imagine that the epsilon is plus or minus 1. And then clearly, when you average over the two possibilities, you get the cosine. And so it turns out to be exact. And this thing is just because the random variables, I mean, the Bernoulli random variables are 0, 1, rather than 1 and minus 1. But the point is that what do we learn over here? Well, if you know this function as function of h, you know the Fourier transform of the random variable y, which means that you know the random variable y. And the question again is, does this characterize the random partition? So we can reformulate the question here, saying that suppose we know the distribution of y, do we know the partition, the whole partition x1 and so on? I mean, in terms of distributions. And well, you can suspect that it's a bit asking too much, but we only consider residual allocation models. So in fact, we are only, I mean, everything depends on the distribution of the first element of the random partition. If you know the law for x1, for the first one, well, I'm thinking now for gem, in the situation of a gem. So if you know the distribution of x1, then you know how to construct the whole remaining partition using the stick breaking or residual allocation construction. So suppose we know y. Do we know the law of x1? And the answer turns out to depend on the parameter p. If p is different from 1/2, the answer is yes. And if p equals 1/2, it turns out that we can construct examples where we have two distinct residual allocation models, but with the same Bernoulli convolution. Let me just mention for those interested in this kind of structures, there is a very nice review by Pittman, which also discusses things in a greater context. And to point out that we cannot completely expect a positive answer always. Here is actually a very nice example. Consider the Brownian bridge between you start at 0 and you must end up at 1. Well, you know that the crossing times are a little bit messy to define, but let's not worry too much about it. One can define them, or we can discretize and look at the limit. So we can look at all the times we have crossed, and this gives a partition of 0, 1. It so happens that this random partition is a Poisson-Dirichlet distribution, but a two-parameter Poisson-Dirichlet distribution, so parameter 1/2, 1/2. I'm not going to explain how it is defined. So here but it's definitely distinct from all the Poisson-Dirichlet distributions we have checked. Now we look at the time spent up. So for instance, here we have some time up, some time up. I mean, we have to consider this, and so on. Now you all know those properties of the Brownian bridges about reflection. Suppose you do these kind of things, you continue here. Then the next step can be up or down with equal probability. So in fact, if you condition everything on having this crossing time, so I mean these times where you touch the 0 line here, then for all those excursions, you can be with equal probability up or down. So the time spent up, given a partition, corresponds to basically choosing a Bernoulli random variables for each interval. And with probability 1/2, it's 1, or probability 0, probability 1/2, it's 0. So the time spent up is the Bernoulli convolution of this random sequence here. And what is known is that the time spent up is the uniform random variable. And then one can do those calculations, and one knows that one can check that the uniform random variable is the p equals 1/2 Bernoulli convolution of Poisson-Dirichlet of parameter 2. But here it's also the one of Poisson-Dirichlet of this 1/2, 1/2. So the point here, we see that we have two distinct measures on partitions with the same Bernoulli convolution. So the Bernoulli convolution is not enough to characterize the partition in this case. Okay, so this is one example. There is a further example, counterexample due to Alexander Oroy. Yeah, I have time to look at. I still have like 10 minutes, a bit less, 5. All right, so I'll spend not too much time. This Oroy's example is kind of nice because what we could say is that suppose we know the laws of the Bernoulli convolutions for all p's, not only for one p, and we try to reconstruct the law for the partition, but suppose we have it for all p's. Perhaps now we can characterize the partition. But Oroy says no, because of the following example. Here we have a partition with only 3 elements. So we have those 3 random variables between 0 and 1. They add up to 1. And we consider the Bernoulli convolutions like that. Now, little f is the probability density for these partitions. It's a function of only the first 2 parameters, because x3 will necessarily be 1 minus x1 minus x2. And then, okay, so then Oroy says that suppose that you know the laws of y for every single p. So for, I mean, if you change the parameter p for Bernoulli, you change the law of y. But suppose you know the laws of y for every single p, then still f is not unique. And the reasoning is like that. So if you look at the law of y, it depends on the marginals of this function of f. When you only look at the law of x1, x2, or x1 plus x2. So if you don't know the whole joint distribution of x1 and x2, but only those marginals here, that's enough to know the Bernoulli convolutions. So now we wonder whether we can find another f tilde, another distributions on x1, x2, which has the same marginals for x1, x2, and x1 plus x2. So in other words, you want those relations. You fix x1, you integrate over x2, and for f and f tilde, and you get exactly the same for all x1. The marginal when you integrate x1 and you retain x2 is over here. And when you look at the marginals with x1 plus x2, so you fix x1 plus x2, and then you'd like to say that otherwise you get the same thing. So it amounts to getting this kind of integrations. So now the Oroy's idea is to say that, okay, this is x1, this is x2. So now we have some probability density function over here, function which has support over here. Now let's look at a box over here, and in this box here, which we divide exactly like the picture shows, and we look at the function which is 0 here, -1, +1, according to whether you see both signs. And you just make it small enough, so, and you also select it at the place where the function f is strictly positive, so that you can add this function g, and you still have a probability distribution. And then the point is that when you integrate, for instance, like that, the marginals, then over here, you can check that you're going to pick up some minus, 0, and some plus. But the plus is going to compensate the minus. So the marginal here is the same. The marginal like that, also, you can check that you always have cancellations of the plus and the minus. And now in diagonal also, because if you have something like that, you have some minus and some plus. So it's very clever. I mean, I really like this counterexample. So it shows that you can find two different f and f tilde with the same marginals over here. And then you can check that all the Bernoulli convolutions, no matter what P is, only depends on those marginals. So then they cannot distinguish with f and f tilde. All right, so I have 2 minutes to discuss open questions. I mean, natural open questions. Elbow slide prove these beautiful results in dimensions 5 and higher. What about 3 and 4? Much harder, but it should still be true. To have Poisson de Richelet, so much more information than just the fact that we have a probability of long cycles. On Z2, I mentioned this result about proving that this was, I mean, had the polar bound with the distance between X and Y. There is a conjecture due to Polyakov for quantum spins, but the translation here to this probability model is that the decay should be exponential. And this is, it's not even totally clear that this is true. And assuming it's true, what about parameters theta which don't correspond to these quantum systems? It's really a delicate question. Something which we don't have and which should be there, some monotonicity properties in theta and beta. More beta, you should have more long cycles. Larger theta, you have more cycles, so they should be smaller. So is it true? Nothing has been proved. Another question is whether there could be a way to directly prove that this cycle structure has the property of being a residual allocation cycle structure. But in a finite graph, even on the complete graph, that's not true. But can we prove that as the number of vertices goes to infinity, this would be true? And then we could use this much simpler way of characterizing random partitions. Then on the complete graph, something that we are working with Jakob right now, one can prove, for instance, this expectation of, more than just a product of a cosine or cosh. We can mix this with a sinh function. And so this gives a bit more information than we were using. So can we use that and get closer to Poisson de Richelet? And one can even prove, at least we have a quasi-proof, that if you take the expectation of moments, then this is given by the Poisson de Richelet moments. But it's not for all moments m's, but only under lots of restrictions. So theta needs to be 2, 3, and so on. The moments must also be greater or equals to 2 integers, and the sum must be less than theta. So is it enough to characterize the whole thing? It's hard to imagine that it's not, because if you think, if this is given by a nice formula like this one for many m's and thetas, it should be the same formula always. And if yes, then this is the formula for Poisson de Richelet, and that we should be able to conclude. So just, I'm sure that Peter is getting impatient. So I discussed product of random transpositions, and we were looking at the random partition coming from the cycle structure. And in some cases, we have access to some things like the expectation of a product of cosines involving the cycle lengths. And this gave us this link to Bernoulli convolutions and the question whether we had enough characterizations. There are lots of open questions. Thank you very much for your patience.
Thank you, Daniel, for a very lovely talk. The floor is open for questions. If anyone would like to ask questions, just feel free to unmute yourselves and ask, or if you prefer, raise your hand via Zoom while we wait for that. I do have a question which you sort of kind of answered already, I think 2 slides ago with your open questions. But this monotonicity in, let's say, theta, is there some reason why this is not sort of immediately apparent that it should be monotone?
Well, I mean, you increase data, so then you have more cycles, but to decide that 2 points have a smaller probability of belonging to the same cycle, I don't know what to say. Nobody has proved anything.
But sort of the intuition says that it should be monotone, right?
Yes. Yeah, you tilt everything towards having more cycles, and that's it. So they should be smaller.
Mm-hmm. But there's
yeah,
no negative correlation that would sort of imply that this argument breaks or something.
No, nothing has been shown so far.
Okay, thank you. Jan has a question.
Yes. So several times you said this has only been proved for theta is 2, 3, and so on.
Mm-hmm.
Does that mean that these proofs basically go back to the quantum world and prove
That's
things
right.
in this quantum?
Yes. So these are typically results on the complete graph, and then we can use several tricks. I mean, for the quantum Heisenberg model, it's just a question of addition of spins, so it's not so hard to do these calculations. And for larger spins, it's actually much more involved. I think it goes back a little bit to this Diaconis Shashani. Certainly, I mean, Jacob is the expert. He is using a lot of group theory to get several non-trivial expressions. But the calculations are possible.
Thanks.
All right. Any other questions? If not,
I have just a.
yeah, go ahead.
Sorry, I have a stupid question. I somehow learned about it only in last minute. So, can I watch it all from the beginning somewhere?
So it's
Yes,
been
it's all on
recorded.
YouTube.
It is on YouTube somewhere.
Yes, if you go to the website of the probability seminar, we record all.
Okay. Okay. Okay, I will find it. Fine. Thank you.
All right. So yeah, thanks again to Daniel for this lovely talk. We'll take maybe a 2 or 3 minute break and then reconvene when Cécile will give her talk on, what was it? The topic, Cécile?
Yes, it's a two-table theorem for a disordered version of the Chinese restaurant process.
There we go. Hopefully no one's too hungry yet.
So we have 2 minutes. I'm going to get
Yes.
some coffee, and we'll be back.
Cécile, if you want to prepare everything.
Yeah, let me share my screen and then I'll get some water.
Mhm.
Jané?
Ano.
No. Ahoj, já jsem ve Františkových Lázních teďka.
Jo.
Milátka měla operaci kyčle a my jsme teďka jako ve Františkových Lázní. Takže já se v Praze neobjevím až někdy 8. prosince nebo tak nějak.
Jo. Možná ti zavolám, abychom to nedali všem, než by nám rozuměli.
No. Tak já se ozvu, až přijdu do Prahy, měli bychom se setkat nějak. No.
Roman, if you want, so I just shared the link to where the stream is available, and you'll be able to watch it there.
Okay. Okay. So I should copy it somehow, or what I should do?
So the link in chat, if you see it.
Okay, there is chat somewhere. Here I see something. Okay. Show chat.
And you should see a link to YouTube there.
Well, I do not quite see. Fit to window.
If you want, I can also send it to your email.
Ah, now I see it. Okay, now I see it. Fine. Thank you.
All right. You're welcome. Okay. Cécile, ready to resume?
Yes.
All right. Let me just double check that everything is still streaming as it should be. Yes. All right. Then welcome everyone who's still here or who potentially recently joined us for the second part of today's seminar, where Cécile Mailler will be talking about the two-table theorem for a disordered version of the Chinese restaurant problem? No, process.
Process, sorry, my handwriting. Yes. Thanks a
The floor is yours.
lot. Thanks for the invitation. It's really a pleasure to be here. And it's a pleasure in particular to tell you about this joint work with Jakob Björnberg, Peter Mertes, and Daniel Ueltschi. And at first, I thought that the only common point between Daniel's talk and my talk would be the list of authors, which intersects quite a lot. But no, it's also going to be about the Poisson d'Iréchlé and GEM. So that's great. And also, I'm going to gain 2 minutes because I don't have to redefine them. So let me dive straight in by defining the model. So I'm first going to define the model and hopefully later kind of discuss the context. But first, the model. So definition of the model. So it's a model that depends on two parameters. The first parameter is mu. It's a probability distribution on the half positive line. Here we go. Oops, sorry. Half positive line. And the second parameter is just a real positive number, theta. And that's the only two parameters. So now I'm going to tell you how we define the disordered Chinese restaurant process. First, we sample a sequence WI, which are going to be the table weights. So it's just an IID sequence of distribution mu. So these are all IID random variables, all distributed according to this mu, and they are called table weights. And hopefully the reason why is going to become clear quite soon. So we define this restaurant as follows. So you have to imagine it's a funny type of restaurant because it's an infinite restaurant. So it has infinite capacity and the number of tables is just unbounded. And also the number of customers that can sit per table is also unbounded. So it's a bit of a strange restaurant. And you have to imagine that an infinite list of customers numbered 1, 2, 3, etc. Are going to enter the restaurant one after the other, and they're going to choose where to sit with some probabilistic rules. And to tell you about the probabilistic rules, it's better to imagine that a few customers have already entered the restaurant, because the first customer is always going to sit at the first table, which has weight W1. So the first customer is always going to sit here, so it's not very interesting. But let's imagine that we already have customers 1, 3, and 4 sitting at table 1, and customers 2 and 5 sitting at table 2. Table 2 has weight W2. And then we have customer 6 is trying to enter the restaurant. And I'm going to tell you with which probability is going to sit where. So the sixth customer is going to sit at an already occupied table with probability proportional to the weight of that table times the number of customers already sitting there. So it's going to sit to the first table with probability proportional to 3 times W1, and then there is going to be a denominator, which I'm going to write later. It's going to sit at the second table with probability proportional to 2 times W2, because there are already 2 customers sitting at the second table, and it's going to open a new table, which will be table number 3, with probability proportional to my parameter theta, which is the second parameter of my model. So now these are all the options, so I can write the denominators, which are going to be just the sum of these 3 things. So 3W1 plus W2, 2W2 plus theta. So 3W1 plus 2W2 plus theta, 3W1, 2W2 plus theta. Okay, and so on and so forth. So then, you know, customer 6 decides to sit somewhere, and then customer 7 just applies the same rules to decide where to sit. Okay, so that's the model. If it's not clear, please, you know, ask questions in the chat or unmute yourself and ask. And the quantity we are interested in are the sizes of the tables. So Si of n will be the size of the ith table. The order of the table is just the order in which they are open. So, okay, in the order in which they appear or they are occupied. So the size of the ith table at time n, and time n is just when there are n customers in the restaurant. Okay, so we're interested in this list of sizes, right? Because this is for all I larger or equal to 1, and for all n larger or equal to 0. So we're interested in this list of sizes of tables as n becomes large. Okay, and so before telling you what we did, I want to tell you about the context, and the context is just the classical Chinese restaurant process, which maybe you've all heard of already, but I'm going to talk about it very briefly. So if mu is just a Dirac mass at 1, which would mean that all the weights are equal to 1, then this is the classical Chinese restaurant process. So this was credited to Pittman, who himself credited to Dobbins. But apparently, so it's due to Dobbins. And I just want, so it has applications to statistics and also to populations genetics. Well, it's just a very important process, I think, with lots of applications. Also, it has applications to studying random permutations. So if you are a bit more careful in like the order in which the customers sit at each table, you can see these as the cycles of a random permutation. But this is not what I want to do, what I want to focus on here. What I want to focus on, talking about the classical Chinese restaurant process, is one result, really, which is the following. If you look, so I told you I'm interested in the sizes of the tables at time n. So if I take this list, S1 of n, which is the size of the first table, S2 of n, the size of the second table, etc. So as an infinite list, and I divide it by n, then almost surely, as n goes to infinity, this converges to a limit, v1, v2, etc. And this list is distributed as GEM theta. So for Griffith, Engen, and McCloskey, so this is the distribution that Daniel mentioned in his talk, which you can build by doing some stick breaking construction. Maybe I'm going to rewrite the definition, but interestingly, I've learned, giving this talk, because people have told me that, in fact, Dario Spano, in fact, told me that this distribution is called GEM because Griffith, Engen, and McCloskey are the people who showed that this convergence is true. So, which I find quite interesting. So just as a reminder, very quickly, recall that the GEM theta is the distribution. So that's the definition of U1, 1 minus U1, U2, 1 minus U1, sorry, times. Sometimes I zoom instead of, here we go. 1 minus U1, 1 minus U2, U3, etc., where the UIs are IID beta 1. Okay, good. So that's the only theorem I wanted to mention, because somehow this is the kind of theorem we wanted to prove for our disordered version of the Chinese restaurant process. And but we also wanted the model to be a bit different, right? We wanted something a bit different. And to make sure things are different, we made the following assumption. So assumption A0. So in this talk, we're going to assume that mu has no atom at its essential supremum. So typically this is not true for a Dirac mass at 1. So an atom is just a Dirac mass. And so we don't want mu to have a Dirac mass at the supremum of its support, which is the essential supremum. Okay? So we don't want the mu to have a Dirac mass at the maximal possible value a random variable distributed like mu could take. Okay? So this ensures that you will always get tables with a larger and larger weight. So as you weight, more and more tables are going to appear, and these tables get a new weight from your list of IID weights. And among these weights, you will get more and more records, better and better ones. Okay, so this is really what we want. And also,
sorry, can I just
yes.
interrupt? But do you allow sort of an infinite support?
We allow an infinite support, so we allow the essential support to be infinite.
Okay, thank you.
Infinity. And in fact, without loss of generality, this essential supremum is going to be called M in the rest of the talk for maximum, if you want. And without loss of generality, we assume that M is either 1 or infinity, because these are really the two essential cases. Either the weights are bounded, and in which case we could say they are bounded by 1 by just rescaling everything, or they are unbounded, and this is a case that we allow. Great. Okay, so let's start with just a proposition, which is very easy to prove. So we prove it in 1 page in our paper. So I promise this is not the core of the paper, but it's interesting because already it shows that under this assumption A0, we get a very different behavior from what was going on in the classical Chinese restaurant process. So the two things are as follows. For all tables, if we look at the size of the table at time n, well, this is not very different from the classical Chinese restaurant process, but almost surely the number of customers sitting at that table goes to infinity. So all your tables are going to become bigger and bigger in the sense that they're going to have more and more customers sitting there. But what's more interesting and very different from this Chinese restaurant process is that if I divide this size of the table by n, sorry, I'm writing the wrong thing. This is going to 0 almost surely as n goes to infinity. So this means that this is very different to here. So here you see if I take the size of the ith table and I divide it by n, this converges to vi, and vi is non-negative almost surely. So in the Chinese restaurant process, this was definitely not true. Okay, so a very different situation. And then the second thing, which really is going to be crucial in the rest of the talk, is that if you look at Bn as being the index of the customer that opened, so when I say open, it's like, it means the table was empty and this customer sat there for the first time, that opened the largest table at time n. So what do I mean by this? I mean, look at your restaurant at time n. one of the tables is the largest. It could be that you have ties. Let's assume we have no tie. One table is the largest, okay? And I'm asking, when is the first time this table was occupied? So in the future, I'm going to call this the birth time of that table. So I'm interested, when was it born? And it's why it's called BN, right? So BN is the birth time of the largest table in the restaurant at time n. And it's easy to see that Bn goes to infinity almost surely as n goes to infinity. So this means that as time goes on, the largest table is going to change with time. So one table might be leading the restaurant for a while, being bigger table, but then it's going to be beaten by another one later. And you can kind of guess that because there is going to be some kind of, in the model, somehow by definition, there is a competition between like the old tables, which have had time to grow, to attract new customers, right? Because the rich gets richer with this model, because the more you have customers, the more likely you are to get customers. But you also get fitter and fitter tables, so tables with higher and higher weights. And these, once they have had the chance to grow in size, they can overtake a past, record. And this is going to keep on happening. So this you can see quite easily, as I said. But I want to tell you what final results we were able to get. But to get these final results, we need more assumptions. So section 2 is going to be about results. So the first assumption we make, and I'm going to spend quite a lot of time on this, is about some extreme value property for the weight distribution. So we assume that there exists two sequences, AN and BN, so just sequences of numbers, and nu non-degenerate I'm going to explain what does that mean, what this means, probability distribution, such that if I take the maximum from I equals 1 to n of the weights, so I take the largest of the nth first weights, I want to say that this behaves like A of n plus B of n times a random variable which is distributed like nu. Or in other words, the equation I just wrote. So you want to control the behavior of the largest of the weight of the nth first weights. And you can see why this is important, because we want to focus on the largest tables in the restaurant, and therefore the largest weights are going to be what matter. Okay, and in fact, so I said I was going to spend some time on this because interestingly, and this is something that I really learned writing this paper, interestingly, this doesn't look so restrictive, but in fact, by extreme value theory, you get much more information for free just by making this assumption. You get actually much more information on your weight distribution or on A of n and B of n and on nu. So let me tell you, in fact, so it's a little bit of a digression, but it's in fact useful in the proofs. So by extreme value theory, and this is, for example, you can read about it in the book by Resnick, but there are lots of other references. There are only 3 possibilities for nu. And to express them, I'm going to introduce a notation. I'm going to let nu of the interval minus infinity x, okay, as being exponential minus phi of x. So this is my definition for phi of x, right? So phi of x is minus the log of the measure of minus infinity x according to nu. And this is for all x in R. Okay, so this is just my definition of phi. So there are only 3 possibilities. The first one is called Weibull. I never know. I think there are 2 L's. Yes, the Weibull case. In this case, phi of x is just x to the alpha indicator that x is negative. So please don't worry about the indicators and the absolute values and the signs, because it's just, you need to, if you change bn into minus bn, it changes the signs and all that, right? So don't worry too much about the signs. But basically, phi of x is x to the alpha. And in this case, you get that, in fact, it's only your weights must be bounded, so bounded weights. And in fact, you get even better, you get a formula for mu of 1 minus x 1. So again, the measure according to mu of the interval 1 minus x 1 must be of the form x to the alpha times the slowly varying function of x, slowly varying at 0. For some alpha positive, I forgot to say about the alpha positive, so before, I should have put it before. Here we go. Oops. Good. For some alpha positive. If you don't know what slowly varying at 0 means, it doesn't matter. You can imagine either a constant or something that varies slowly, a bit like a log. Okay. So, but you have a formula for mu. This gives you a formula for mu. And also you have formulas for A. So A of n is just in this case, constant equal to 1. And B of n is equal to n to the minus 1 over alpha times another slowly varying function of n. This time it's varying at infinity. So I insist on the fact that the two L's are not the same. L is just a generic notation for a slowly varying function. Okay, and this one is slowly varying at infinity. So in this case, we have much more information than what the assumption A1 maybe let you think, would let you think. The second case is the Gumbel case. In that case, phi of x is e to the minus x. And so interestingly, you see in the variable case, I said, oh, there was just, it's one probability distribution here, this nu. But in fact, it's a family, right? Because it's a family indexed by this parameter alpha. In the Gumbel case, it's really only one nu, right? But it's the only good news in the Gumbel case. So the Gumbel case is really the worst one. And in the Proust, it's the hardest one, because this is the one where we know the least about all the rest. So we don't have a formula for mu. M could be either 1 or infinity, which means the weights could be bounded or unbounded. And the only thing we know is that A and B, these two sequences, are slowly varying, but no formula for mu, no formula for A or for B. So this is bad news. I mean, this is where we have the least information. And the last case is the Fréchet case. In this case, phi of x is x to the minus alpha. Again, don't worry about the indicators, but I have to write them, otherwise it's wrong, but plus infinity indicator 0. Again, don't worry about the infinity either. Basically, phi of x is x to the minus alpha. Again, for some parameter alpha positive. And this time is very similar to the variable case, although the weights have to be unbounded, but you get a formula for mu. So mu of x infinity is equal to x to the minus alpha times the slowly varying function at infinity, and only on the positive line. And A of n is just 0, and B of n is n to the 1 over alpha times the slowly varying function of n at infinity. So yes, so I find it interesting. I think the first time you see it, to see that this assumption A1, in fact, gives you much more. And in particular, in the Weibull and Fréchet case, you get a formula for mu, which is super useful in the calculations. And in the Gumbel case, you have a bit less things to work with, but still you get some information about A and B, for example. And I forgot to say why I said non-degenerate here is because if I divide by something ridiculously big, I can always get that converged to a Dirac mass at 0, and I don't want that, right? So I want mu to be reasonable. I want to get some information from them. Good. So these are the three cases, and under this assumption A1, we can prove a first theorem. So theorem 1. Under assumptions A0 and A1, we get that if you look at the maximum from I equals 1 to n, so the largest table in the restaurant at time n, you look at the size of this largest table, you divide it by n, and this converges in probability when n goes to infinity to 1. So this is what we could call a one-table theorem. This means that if you look at a restaurant at a very large time n, a proportion close to 1 of all the customers are sitting at the same table. Okay. But it's quite easy to see that this can't be true almost surely. And this is because I've told you that the largest table will change over time. And this means that there are going to be times when the new, leader is overtaking the old leading table. And this is going to take a long time because, it's going to take a linear amount of time because the customers just arrive one by one and they need to, it takes time for the new leader to overtake the old leader. So then, during these long times, the two largest tables are going to have macroscopic occupancy. So both of them are going to be around, constant times n size. Okay, so why is it true that we still converge in probability to 1? Is because these overtakings don't happen often, and they happen more and more rarely as time goes on. So you still get convergence in probability, but not almost sure. So the question, once we had realized that this was what was going on, we kind of wondered, what if we looked at the two largest tables together? Then could it be that then together they realize this convergence to 1 almost surely? And this would mean, can we exclude the case that 3 tables kind of overtake each other at the same time? And the answer is yes, but to prove it, we need more assumptions. And we need assumption A2. So A2. So in the viable case, we need that alpha is strictly larger than 1. So let me go back to the viable case. I'm going to have to scroll up. So viable was this case here. And I say I need alpha strictly larger than 1. So this is a bit bad news. I mean, yeah, because it means I can't, well, assumption A2 excludes the case of uniform weights. So for the second theorem will not hold for the case when the weights are uniformly distributed on 0, 1. Okay, so I don't know if the result is still true. I just know that we can't prove it. Okay, so this excludes mu being uniform on 0, 1, which is a bit annoying. In the Gumbel case, we need technical assumptions, which I don't want to raise. But I think it is interesting from the digression that I made, you could have guessed that this is where assumption A1 gives me very little in the Gumbel case. And so we need more. And I'm not going to write the technical assumptions that we need because they're a bit ugly, but I can tell you that basically what we need is some speed of convergence of the left-hand side to the right-hand side, basically. So that's what we need, a bit more. We don't need it in the Weibull and Fréchet because we have a formula for mu anyway, so we know the speed of convergence, right? We know a lot. And in fact, in the Fréchet case, we need nothing more, which is quite pleasant. Okay, so let me state theorem 2, which is the main theorem, which, was in the title. So under all these assumptions, A0, A1, and A2, if I look at the size of the largest table at time n, and here I'm using this order statistics notation here. So the bracket 1 means this is the largest of the SIs n at time n, okay? Plus the second largest. So the size of the largest table plus the size of the second largest table at time n divided by n converges almost surely as n goes to infinity to 1. So this means that you will never have 3 tables or more overtaking each other at the same time. But never. As n goes to infinity. Okay, so maybe before telling you about the ideas of the proof, I can tell you a little bit about why we call this the two-table theorem. So maybe some of you have guessed already. So this is reminiscent of a paper called a two-city theorem for a parabolic Anderson model, which is a paper by Koenig, Lacouin, Mertes, and Sidorova. So the methods of proof are very different, but the idea is really the same. So it's a branching random walk in a random environment, And the idea is that the population kind of like localizes in one city. So most of the population at a given time, large time, is all in one city. But then, you know, a few particles of the populations explore and find a better potential, a better city. And then eventually this better city kind of overtakes the old good city. And so you also have this kind of convergence to one in probability. And you need two cities to get convergence to one almost surely, and really for the same reasons. But the proofs are very different because the models are just very different. And the proof is, in fact, more inspired by a paper by Stefan Dereich, Peter Mertens, and myself. And the main idea, Jan is raising his hand. Yes.
Just a silly question. If n increases, then you can look at the table with the largest weight and the table with the most customers. Are they roughly the same?
No, not at all.
Aha.
So not at all. Very good question. Yeah. So they're not the same because the table with the largest weight is likely to be very young. And so it hasn't had time to grow. So in fact, that's a very interesting question. So in fact, all our proofs rely on the question, if you look at the largest table at time n, when was it born and what's its weight? And it's very far from the largest weight at time n. Thank you. Great.
In some tables, even though at some point they are the largest in weight, they will never be the largest in number of customers.
Yeah, so this could be because, yeah, it could be that someone even fitter was born shortly after and overtakes them before. Yeah.
Okay, thanks.
Good. And so the idea of the proof is to embed in continuous time. And to me also, it makes everything much more intuitive, in fact. So let's do that. So we're going to embed. So this is section 3, embedding in continuous time. So it's very classical to do, but let me show you how we do it. So instead of having the customers entering the restaurant one by one, like I had in my definition, we're going to have them enter the restaurant at random times. And we're going to do this as follows. So again, I'm going to do the same case as before. So imagine you had customers 1, 3, and 4 sitting here, and customers 2 and 5 sitting at the second table. And this time we're going to imagine that all these customers are wearing watches, and these watches are clock watches. They're going to ring, and they're going to ring at a Poisson rate, and the rate is going to be given by the weight of the table at which they're sitting. So this, oops, no. So this, sorry, I wanted to write here. Yeah, so these 3 customers here have a red stopwatch that is going to ring at a Poisson rate of parameter W1. Then these 2 customers here that are sitting at the second table, they have a purple watch. And this purple watch is going to ring at a Poisson rate of parameter W2. And then there is a big clock in the restaurant, a green clock, which is going to ring at rate theta. You remember this parameter theta, okay? So, and all these clocks are independent of each other. So then one of them rings, and whenever it rings, the 6th customer is going to enter the restaurant at that time, okay? And if it's one of these red clocks that has rung, then the 6th customer is going to sit at the first table and it's going to get its own red watch that's going to start ringing at the same Poisson rate. If it's a purple watch, then it's going to sit at the second table. And if it's the restaurant clock that has rung, then the 6th customer just enters and opens a new table. Okay? So, importantly, what's important is that, in fact, the 2 processes are the same, except that here we have these random times. But what I mean is that, let me just introduce some notations here. But if I let Sn be the time of arrival of the nth customer in the restaurant, and if I let Zi of t be the size of the ith table at time t, then the process of the list, if you want, Z1, Z2, etc. at time Sn as a process is equal to the process S of n in discrete time that I defined at the beginning of the talk. So, and in fact, this is true in distribution, but you can couple them so that is true almost surely. So what it means is that if you take your process in continuous time and you have someone taking a picture of the restaurant every time a clock rings. So when a clock rings, I take a picture. Then there's another clock ring, I take a picture. And then I have this sequence of picture, which is a discrete, time process, the first picture, the second picture, etc. This is exactly the discrete time process that I defined at the beginning of the talk. And this is just because you're using Poisson rates, right? So nothing surprising. Good. So it's the same process, but here normally you're thinking, but Cécile, why have you've just made things more complicated, right? And indeed I have, because this process of Sn is highly non-trivial. It's very difficult. And in particular, also the inverse of Sn, which is the n of t, the number of customers in the restaurant at time t. So this is, if you want, the inverse of this process Sn. This is also very difficult, right? I mean, at first, I can't tell you how it behaves as t goes to infinity. At the end of the work, at the end of the paper, we can say things about it, but it's highly non-trivial. So why did we do this? Well, we did this because we gained a lot of independence. So what do I mean is that if you just want to know the size of the first table, at time n, you can just focus on the first table and ignore all the rest. Okay, you can just, just like ignore the rest and focus on the first table. And what you see is just a very simple branching process called the Uel process of parameter W1. So I'm gonna write this more rigorously. But before also, the second very good news is that if you look at M of t, which is the number of tables opened at time t, this is just a Poisson process of intensity theta. So this is super easy because this is just governed only by this green clock, which rings at a Poisson rate of parameter theta, and every time it rings, it adds a new table to the restaurant. So this also becomes very easy now. Okay. So, as I said, we gain independence. So now we have Zi of t, which is the size of the ith table at time t. This is just a Uel process. So these Uel processes here are going to be IID Uel of parameter 1. But I've told you that the ith table should be a Uel process of parameter Wi, right? But to do that, I just need to multiply the time by Wi. So this is fine. And then I just need to say, well, be careful that table I was not born at time 0. So I need to shift the time by tau I, which is the birth time of table I. Okay, and this is just the Ws are just the weights. So I'm going to remind you what a Uel process is in a second for people who don't know, but just a quick comment. So the tau I's are super easy because I said, the number of tables are opened according to a Poisson process of parameter theta. So the tau I's are just the points of this Poisson process of parameter theta. Okay, so the difference between two consecutive tau I's are just exponential of parameter theta. The Wi's are just IID weights. And the Yi's are just Uel processes. So what's a Uel process? The Uel process is the simplest branching process you can imagine, really, I think. Or at least the simplest I can imagine. So this is time. And you have to imagine you have one particle. And this particle lives for an exponential time of parameter 1. Okay? And when it dies, you can imagine that, in fact, it continues to live, but it gives birth to another particle. And both these particles now will also just reproduce after an exponential time of parameter 1. So let's say it was this one, it gives birth to a new particle, and so on and so forth. Okay? So all the particles reproduce at rate 1, and when they reproduce, they just split in 2. Okay? And what's really nice about the Yule process, I'm going to write here as a lemma, is that you know, well, I'm going to write what we really know, but in fact, we know much more, and we need a bit more in the paper. So if you take your Yule process and you renormalize it by e to the minus t, it's a continuous time martingale, it's non-negative, and it converges almost surely thus to a limit as t goes to infinity. And this limit, it's a very nice proof, is exponentially distributed of parameter 1 as well. And yes, and we need a bit more in the paper. We need, I think, some kind of uniform convergence or something over t, but you can basically, I often say to people, it's incredible with the Yule process, you can basically imagine that this limit is unequal. I mean, it's not true, but all your wishes are granted with this limit, I feel. Anyway, it converges very quickly, very robustly to an exponential of parameter 1. Good. Yes, Jan.
So maybe I'm skipping ahead of something, but does that mean that somehow part of the randomness does not matter? That,
yeah,
in a sense that you only need to know in which order these weights arrive, and then actually the randomness of how many customers come at a given table is not relevant for who is the biggest table at a given point?
Yeah, so the kind of randomness coming from the Yule, it is basically deterministic. And we can...
in long enough time, of course.
In long enough time. And, oh, something went wrong. Can you still see my screen?
I do.
Okay. I can't see my screen. Here we go. I'm back. Good. Great. Yes, so let me in fact make that clear now. In fact, that's indeed you're making my transitions look very smooth. So the idea, we can write Zi of t as being approximately equal to xi I times e to the wi t minus 2i. So we can see this as a decoration. Of course, at the end of the proof, we do need to show that they don't do anything silly, right? But what's really important is what we call the exponents. And basically, the proof goes as follows. We just prove a 2-exponent theorem, and then we show that the 2 tables corresponding to these 2 largest exponents are the 2 leading tables, and that the xi's don't matter too much. Okay, so I almost forgot. The first time I gave this talk was in front of Daniel, and this is again in front of Daniel, so I can't get it wrong. I didn't do this picture that I'm about to draw, and he told me off. So I'm not doing it again. I'm doing the picture, which is indeed very interesting. So it was a very good constructive comment. So we're interested in these exponents, and these are so simple. So let me write them. So you have time here. So you have the 2 i's. So 2-1 is here, 2-2 is here, 2-3 is here, say, 2-4. And then the exponents are just linear functions with random slope, which is given by the wi's. And so, say 2-1 is here, 2-2 is lower, 2-3 bigger, 2-4 has no chance, etc. And so, yes, so here, to me, this is where it becomes very clear that basically if a table has a high weight, it's going to beat any table with a lower weight. Okay, but it's also clear, to come back to your first question, Jan, that you need some time to overtake. So if a linear function is already quite high, but you have someone with a very high weight that is born, is going to need some time to kind of overtake the old leader. And you can really see this competition on the exponents, and we kind of got rid of the noise coming from these Uel processes, which is not important. So let me just finish the talk by doing one kind of like back of the envelope calculation, which is really how we start writing the proofs, or we start guessing what's going on. So it's going to be a bit hand wavy, but bear with me. So we need to understand the largest exponents, right? Or tables, but exponents, let's say, at time t. So the question is, when were they born? And what's their weight? And this is basically the heart of the proof. So we're going to say, let's say, so I want to find this information. So I'm going to say, let's say I was born at a time constant times some function ut, and the aim of my calculation is to find ut. Okay, so it's normal. You don't know what ut is. It's just a notation. The aim of my calculation is to find ut. Is it square root t? Is it log t? You know, what's it? And if I was born at time ut, approximately, if I want to be competitive in the long run, I need to have one of the largest weights available at that time. But I know what these are. These are A of the number of tables open at that time, plus a random variable, but let's say a constant here for this calculation, times B, times the number of tables available at that time. This is because of my assumption A1. So assumption A1 is telling me the largest possible weights at time ut are of that order. Okay? And if I want to be one of the big tables, I need to have one of the largest possible weights available at the time when I was born. I need to have been lucky when I picked my weight. Okay, so then what's my exponent if I have these properties here? Well, my exponent is just, so t minus 2i. So it's my weight, AUT plus WBUT times t minus SUT. So we do the calculation and we get t times A of ut plus WTBUT minus SUT A of ut plus a last term which doesn't matter. So what's interesting is that in this calculation, you can really see this competition I told you about. Here you can see the advantage you get by having a high weight, so by being fit. So by having an unusually exceptionally high weight, so not only you got a weight of the order of the largest weight available at the time, but you were really lucky. You're really like among the really best ones. So your W is particularly high. This gives you an advantage for your exponent here. But you can also get a disadvantage if you were born too late. So if you're a bit too young. So this is a disadvantage you get for being too young. Okay, so you have this fight between these two things. So again, being too young within that window of like optimal time, right? But anyway, you were born a tiny bit too early. And so basically the guess that we make, and then we prove it works, the guess that we make is that these two things should be of the same order. They should balance out. So the correct choice for UT is that TBUT should be equal to UT times A of UT. So this is an implicit equation, but we can show there is only one solution. And in fact, we can calculate it in some examples. So for example, in the variable case, we get UT, which is T to the alpha over alpha plus 1. So we can tell you, if you want to be one of the largest tables at time t, you need to be born at time t to the power alpha over alpha plus 1. And that's basically the proof. And you can see also that the leading term here, this t times A of ut, tells you also, so from all this, we also get that the total number of customers in the restaurant at time t, I told you it was difficult to get, but now we know it should be of the order e exponential to this largest exponent, and so it's of the order e to the t a of ut plus smaller order terms. So somehow this is this calculation, and then the methods we use are actually point processes methods. So we can have a point process, which is basically the process of the towis and the wi's. So it's a two-dimensional point process. It's a very simple one because the towis are just Poisson theta, the wi's are just IID, but we are looking at a very complex functional of this simple point process, and we just need to do complex calculations to kind of understand this functional. But this is basically the proof. And I wanted to maybe end on some open problems. So one of them is quite obvious. So one open problem would be to get rid of this, in the Weibull case, to get rid of this alpha strictly larger than 1. So I'm not sure if we actually need this assumption. At the same time, one could think that if alpha is very close to 0, this means your weight distribution is close to a Dirac at 1. So you're close to the Chinese restaurant process. So then it could be that you have more than 2 tables overtaking at the same time, overtaking each other at the same time. At the same time, for alpha equals 1, I don't know. I mean, yeah, well, the answer is I don't know. It's an open problem. But yeah, there's an interesting, maybe interesting things to understand here. And the second open problem is Daniel's favorite. So it's going back to this picture here. Can we understand the point process of all these green points, which I have only one here on the picture, but the times at which you have a leader change. So I told you these are going to be rarer and rarer, but we don't really understand them as a point process. We don't really, yeah, we tried a little bit, but we can't really say anything about it. So trying to understand this kind of delayed record process would be an interesting open question. But I will stop here, and thanks a lot for your attention.
Thank you very much for this very lovely talk. As always, floor is open for questions. We had a couple by Jan already during the talk, but if there's any more questions, just unmute yourselves now and ask. While we wait for people to maybe come up with questions, I have one which perhaps you've sort of already explained it, or maybe it sort of trivially follows from the fact that you're sort of looking in the limit as t goes to infinity, I guess. But what's preventing the situation where one sort of table gets born that will eventually overtake, and before it overtakes, a second table being born that's even better, so that you could have, in theory, a time where 3 of them are sort of proportionally all non-negligible?
Yeah, so no, so I mean, so I think the two things you say are a bit different. So it's completely true, and this was, I think, Jan's first question. It's completely true that here, for example, let's say this table that I kind of drew here, is, very nice and will overtake, but it could be that someone is just born just after with a tiny bigger weight and, just gets better. Does it make sense? Like you can be beaten. Yes. Even if when you're born, you're the best chance at being the future leader, it could be that someone just steals the position because they're okay. So this could happen, but what we show is that is more like these overtakings at the top here. So,
so my question is, what's preventing the thing you just drew with the 2 being born one after another, for them, for example, to be born a bit further apart in such a way that the overtaking happens essentially at the same time as they both overtake the previous record holder?
Yeah, well, I think it's just very unlikely. So you're basically
it happens, but so unlikely that.
Yeah, I think we're basically that's the proof, right? So we prove that it's very unlikely that you have 3, because you can see it's going to be unlikely. Like you kind of need, all the weights and all the times of birth to be perfectly aligned, so that they cross at the same time.
Yes, but at the same time, if you just want sort of all three of them to have positive proportions, you have a relatively large region around that where this is true, no?
No, not that much, because I think so you have the exponential here that kind of make all the differences bigger.
Okay.
So on the picture with the linear curves, the exponents can be relatively close to each other because all the differences are blown up when you take the exponential.
Mm-hmm.
And again, so that's part of the proof. So in fact, we don't prove it. When I said it's true, when I said we prove a two exponent theorem, it's not quite true. We just prove that the largest two exponents, the third one is low enough, basically. That's what we prove. And we have enough margin to allow us to kind of control the decorations.
Mm-hmm.
But yeah, I mean, I think on the linear, yeah, basically there are going to be crossings a bit like this, but we can show that there is enough space here between the second and third exponent so that when you blow it up with the exponential, it's enough.
Mm.
But yeah, that's a good question.
All right, thank you. Are there any other questions?
Yes. Yeah, thank you very much, Cécile. It was really delightful to hear this talk. I love this model. I have a very simple question. So it's well known that the Chinese restaurant process, or even the branching, the multi-type branching process that you showed, in the case when mu is equal to the Dirac mass at 1, is the let's say the time change of the if you change time, if you reverse time twice, and you add also a random time change, you get the Moran process with neutral mutations under the infinite allele model. Do you know that?
No.
No.
Sorry.
So my question is whether actually, so let me tell the equality in terms of the stationary distribution. The Chinese restaurant process is known to be the stationary distribution of let's say in population genetics.
Yes.
When you have neutral mutations and each mutation gives rise to an allele that has never existed in the past.
Yes.
In the limit as t goes to infinity, you get exactly this distribution where theta is the mutation rate, right?
Yes.
So my question is whether you think that your results gives the stationary distribution of a Moran process with selection, where the selection coefficient is exactly the WIs. So theta gives you basically the mutation rate, and each time you have a mutation, you have a new mutation, you have a new fitness, which is the WIs. Okay, so I guess you could be right, but since I don't know so well, this limit thing, I'm not sure. But it is true that here, I mean, that's why you're asking the question. I think that the WIs act as a kind of fitness. So it's like how fit your mutation is means they reproduce quicker. So I mean, I guess, my answer is if you think it's true, then probably. Okay. Sorry. Okay. Yeah. There's actually, it's true. If you look at the Chinese restaurant process, you can if you reverse time and you multiply the rates when you have k lineages instead of having this immigration at rate theta and your branching rate at rate k times at rate k, or here k times wi. Yeah. You multiply by k. Yeah. Basically, you random time change, and it's like having a Kingman coalescent with per lineage mutation. So yeah, we can discuss that. Thank you very much. No, this would be very interesting. Yeah, thank you.
All right. Do we have any other questions? Guess not. Well, Cécile, thanks to you. And again, thank you, Daniel, for your contributions today. The next seminar is going to be in 2 weeks' time, as usual. And